I kind of rely on like I was saying before, my peers to kind of help me with feedback. And if I'm not making sense on something, to not necessarily call me out, but to say, hey, can you explain that in a different way? Because adults can do it in a way that doesn't come off as offensive typically. You know, a kid will be like, I don't understand a word you just said. You know, and maybe not elementary school kids, because they're still like little sweethearts in most cases. But once they hit like fifth grade, sixth grade, which is, you know, beyond the scope of this course, but, you know, it's still worth having a conversation. They start developing the attitude where it's like, I don't get it. I don't understand what you're talking about. And it's like, whoa, relax there, Tiger. You know, so, you know, just having that nice way of giving the feedback is always going to be a good thing. But rounding, that's always been a trouble spot for many students because of the place value chart, like not having a sense of what the names are of the different places within a particular numerical value. And my son's in fifth grade now, so I'm kind of living this curriculum, and it's sort of funny because you know, I try to keep my comments to myself, but when my son comes home from school and says, you know, like in second grade, third grade, my teacher said we should do this, we said we should do that, and you know, like whatever, my thoughts usually go to, oh, okay, yeah, that's good. That's kind of that sound strategy. That's what I would have done. But more often than not, it's like, I don't know that I would have done it that way, but I keep my thoughts to myself, you know. But one thing that you really do need to kind of hit hard when it comes to rounding is the terminology and the vocabulary, right? And then also the rationale for it. Right? So, well, I'll read the blurb here. Why do we round numbers? There's several schools of thought behind the idea of rounding. One thing to always keep in mind is that we don't just round for the sake of rounding. You should always have a valid reason for rounding, right? And so if you can't come up with a good reason for why you're rounding, then don't round. Right? That's what it comes down to. Now, some of those reasons could be sacrificing accuracy for brevity. You know, if I say, you know, I have the example here, but the classic case involves money. If somebody asks me, hey, how much did that TV cost? I don't think they're asking for the exact numerical value. Right? They just want a round number. So, yeah, about $300. All right. Now, if I say $298.72 after tax, did they gain a better understanding of the value of the TV? No, of course not. It's still around $300. I wasn't wrong when I said that. You know, same thing with the example here in terms of salary. Writing an approximation for a more accurate answer. This one confuses people a lot. Starting with the very first moment that they learn rounding and all the way through their adult lives, they tend to interpret this as, okay, so I could just use the rounded answer. So if I do a complicated calculation and I come up with an answer of 17.92815, blah, 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 all these decimal values, what I can do is I can write down 19.78 on paper, but I should still have that full-blown, disgusting decimal somewhere, all right, in my computer, on my calculator, just stored somewhere. Because if I need to take that number, like the answer to part A of a question, and use it in part B, like, okay, now take that number and multiply it by 100. All right, that's cool. You might come up with 1978, but actually it's really going to be 1978 point all of those decimal values that we just kind of lost track of by rounding, right? So it's a matter of saying, yeah, you can write down a shorthand rounded version of it, but you should still also have access to the full-blown decimal. The only exception to that is if you have arrived at a final answer in a word problem or some sort of calculation. Yeah, it's not an intermediate step. It's the final answer. You're not doing anything with this number beyond what what you see. And in the question, and that would be the end of it. Then you can round it. Right? If you've ever seen the movie Office Space, great movie. It's like one of those cult following movies, but it's exceptional. If you haven't seen it, I recommend it. It's just funny. I think Jennifer Aniston's in it, if that matters to some people. If you didn't know, because some people just need to know who's in a movie in order to want to see it. But yeah, one of the themes was that they were robbing a corporation, but sneakily, and so they were taking into account that the banks, when they do financial transfers, they lose track of all the little decimal points after a numerical value. So if they transfer from one account to another, like let's say $378.22.5, they lose track of the 0.5 cents. All right, they lose that because they just round it down. Right. So what they were saying is we could steal that 0.5 cent, because what the company was doing is making thousands of transactions on a daily basis. So hundreds, thousands, maybe 10,000 transactions on a daily basis. So that fraction of a cent is going to add up repeatedly. And they, the company wouldn't notice it missing, but they would obviously notice it because they'd be rich, over time. They obviously, because it's comedy, they screwed it up and they ended up in hot water, but that's spoiler territory. So anyway, the moral of the story here is that extra decimal value meant something, even though it wasn't being reported. It was still happening behind the scenes to the point where people could actually steal that. So, if you're going to explain that to a second grader, no, but you should have an understanding of it if you're going to actually teach it, because when you're teaching math, the one answer to, it's a question that is always framed, but it varies from topic to topic, and that is when are we ever going to need this? And so you got to have an answer in your pocket, otherwise you lose your class very quickly. And I remember one of my colleagues, when I first started teaching, her answer was very simple. When are we ever going to need this? The test on Friday. That's when you need it. Now sit down. That was the end of that. I was like, oh, okay, so I've got to come up with a better answer than that, otherwise I'm not going to last long. But yeah, so come up with what, like I use Office Space. I've been using that example for years. Come up with your own example of how rounding would be important. I feel bad, but I have a really, really terrible example of the importance of rounding and rounding correctly. And I only break it out for mature audiences because it's really wildly inappropriate for a young audience. So the theme of the question is, it's framed as a word problem. So you have a rocket launcher, right? And you have to aim that rocket launcher at a military target, right? So you got to take out that military target. You could even frame it like in a video game or something like that, right? Right next to the military target is a children's hospital, right? So you need to get the calculations for the trajectory of that rocket precisely correct. If you're even off by an eighth of a degree, that's going to knock it off course, and it's going to take out the children's hospital. And I showed the example. I solved it, and it's not even incorrect rounding. It's just rounding. So instead of using the precise value, I use a rounded value. Just by rounding, rocket goes to the children's hospital. By using the precise value, it goes to the military target. So why would I use such a terrible, morbid, horrific example in a class? I really want to drive the point home of just how important rounding is, right? So, but like I said, that example, you want to have kids running out of the classroom screaming and crying, then yeah, break that gem out in a first grade class, So save save that for the adults, you know. But yeah, that's, I mean, speaking to you, not to the young ones. That's an example of how important rounding could be. All right. The third bullet point, rounding to simply, oh, geez, holy grammar. I don't know what I was thinking there. So rounding to simplify mental calculation for the purpose of estimation. Right. So the idea is, and then that's one of the joys of Microsoft Word. If you spell a word so wrong that it becomes another word, it won't pick it up. But yeah, it's rounding to simplify mental calculation. So what the idea is that I want to do mental calculation. I don't want to do like real calculation as in with a calculator. I just want to figure it out on the fly. So instead of, you know, working with complicated numbers, I want to simplify the process. All right. So if I were to say, you know, okay, so how much money am I going to make over the course of a year? Maybe I'm working on an hourly wage. And so, you know, like, and my hours vary from week to week. But, you know, maybe I got a new job and I know that I'm going to work for 20 hours a week, you know, and so I'm working part-time. And it's pretty steady, 20 hours a week. And over those 20 hours, I make, let's say, $300. All right. Well, what I do is I'm really making $317.97. But I'm going to say $300 because I want to figure out what that equates to on a monthly, on a monthly level. So I can take that 300 and multiply it by 4 rather than taking $317.19 and multiplying by 4. You know, I could even go another way and say, okay, well, let's make it 320 and multiply it by 4. Yeah, it'll be a little overestimate, but then I could dial it back a little bit. So I take 320 and multiply it by 4. We're talking 1280. All right, so 1280, but it was an overestimate. So maybe I'll say, all right, well, 1280 is definitely too high because I rounded up. So let's just call it 1250, you know? And so on a monthly basis, that's what I would be either grossing or taking home. But that's a perfectly legitimate reason for rounding. And that's the kind of problem that you sort of want to encourage in those classes. And, you know, looking at my son's homework and also trainings that I've been a part of, you know, whether it's training other teachers or being trained myself, I've found that that it's pretty easy to come up with these examples, word problems. You don't have to go to Engage NY. You don't have to look at Common Core examples. Just take a situation from your own personal life that fits the scenario and just throw it in there, you know? And that's a nice way to kind of acquaint yourself with your students because they want to know about you. And if you can kind of throw yourself into a word problem, that's not a bad thing. But the one thing I will say is you don't want to make it something as simple as, all right, what's my name? My name's Ted. All right. So instead of Tommy is at the supermarket and has $100 in cash on hand, Ted is at the supermarket and has $100 in cash on hand. So what a lot of people do is they take, you know, the Engage NY or the Next Gen or whatever, all those problems that they see online, and they just take, you know, Mary Sue out and they put their kids' names in there. I mean, that's cool. It's a little bit more personal than the question was in its original form, but that's not what I'm talking about. What I'm talking about is like, hey, why did I talk about New York strip steaks for my Labor Day barbecue? Hey, fun fact, I had New York strip steaks for my Labor Day barbecue. All right. Now that doesn't make me unique. I'm sure there are lots of people that had New York strip steaks for their Labor Day barbecues. Right. But that's a point of conversation. Now I can talk about that. Now, did they cost $9.17? No, I just needed nice numbers to make the problem work out. But that's the idea, you know, get the kids kind of invested in you as a person so that they don't hate you. And I really mean this, so that they don't hate you when they don't understand the math, right? Most people, I mean, it's kind of weird. Math and science little different category than every other subject out there. All right. If you're in an English class, if you hate the teacher, it's probably because you have a personality difference or a conflict with that teacher. You don't hate them because of the lack of understanding of, like literature, like it's reading. Maybe you'll have different interpretations of what a article or a book is really talking about, but that's not what's going to cause you to hate them. You hate them because maybe they're just mean people. In math and science, people actually just straight up hate their teachers because they don't understand the math. All right. Sometimes the teachers are mean too. You throw that in there. Sometimes they're just not approachable and all that good stuff. But sometimes it's a matter of frustration kicking in. And it's like, oh, well, this stuff is so hard. Why is it so hard? Because of your face. That's why it's so hard. I hate your face, and that's part of it, and so if you can kind of connect personally with the students, and sometimes it's as simple as, crafting a word problem or two around personal interest, you can connect with them, and so they're less likely to just kind of despise you when they don't get the math. Right? A lot of that's for the older kids, but it still kind of starts creeping in third and fourth grade. That's when the math starts getting beyond the simple, like, add this, subtract that, count this. You start having to do the word problems and the justifications and stuff like that. All right. So how to use place value understanding to round numbers. Process, circle the place value of the digit to be rounded. This is the rounding digit. All right. So if I'm rounding to the nearest tenth, I would circle the tenths place. All right. If the neighboring digit is less than 5, then you keep the rounding digit the same. This is called rounding down. If the neighboring digit is 5 or greater, increase the rounding digit by 1. This is called rounding up. That's the good old, if it's 5 or above, give it a shove. If it's 4 or below, let it go. So if you've ever heard that little gem from back in the day, this is the theory behind it. When rounding to the left-hand side of the decimal, all digits to the right side of the rounding digit will become 0 up to the decimal point. All right, so that's a weird one. When rounding to the right-hand side of the decimal, drop all the digits to the right of the rounding digit. So we'll get into that in a couple minutes. The rationale for the above process basically falls into the umbrella idea. Which number is the value closer to, this or that? And so there's really nothing to the blanks other than to say that there's going to be two values that the number is going to be closer to. So if I say, for example, and I'll just kind of jot it in here just off on the side, just a quick example. We're going to round 10.32 as, oh, I went down there for some reason. That's pretty strange. Round 10.327 to the nearest 10. So the first step in this process it's not even a step, it's just a recognition. Just a question of, do you know where the 10th place is? And so if you do, then you're half the battle is already won. Let me clean up that a little bit. So that's my 10th place. And so I'm looking to see, all right, well, that 10th place could go up to a 4. It could stay at a 3, or I suppose it could go down to a 2, which really wouldn't make sense. But I'll put it in there anyway, because this is sort of a ladder. It's a variation on the ladder concept. All right. So if you've ever seen the ladder technique for rounding, this is kind of like a shorthand way of doing that. All right. And so what the possibilities are would be you could stay put or you can increase in value. All right. but I just put the number below that just because it sort of felt right. So anyway, I'm going to look at the 2. Right? That 2 is my benchmark. If it's 5 or above, then we give it a shove on up to 4. If it's 4 or below, we let it go. So this is less than 5. Oh, that is not the word less. Less than 5. All right, so that's telling me to stay put at 3. All right, so the rounded value is going to be 10.3. All right, so this question here where it says which number is the value closer to this or that, in this context, it's really just asking, is it closer to 10.3 or 10.4? I'll take it as a typo. I'd like to, in the future, have this example on this in this position. So if somebody wants to submit this for a typo bonus, you can do that. First one, first come, first serve. So let me just jot this down in the form of a number line. And like students are very resistant, and I get this in all, I'll say all walks of life, but different age groups. They just want one way to do it that always works. Okay, but we have different learning styles. Different people want to learn things different ways. So you have different learning styles, like the strengths related to your ability to learn, and then also your learning preferences, the way that you want to learn. Right? Most of the time, the learning preferences don't involve drawing a number line, but it's a good way of justifying your work. It's a good, so when those Common Core questions, next gen questions say, justify by showing, with words, pictures, numbers, words, and pictures, or pictures, depending on how it's phrased. That's part of the fun. So you need to have some sort of visual way of making the description, right? And so the picture is worth 1,000 words, right? And that's what somebody said at some point. So here's 10.3. Here's 10.4. So that 2.7 that follows, you got to think of that as if it's covering the span between 10.3 and 10.4, that means that we have 100. You can break it up into 100. It's a 2-digit number. So you can break this up into 100 units. All right, so I can go here and we would say that this is 100 units. Now they're really micro units because it's not units of like whole number values. You can define a unit any way you want. Like you think about units of measure, it could be inches, feet, miles. It could be like a micrometer. It could be super small. It could be super huge, right? But that 27, that 2-digit number of 27 is going to fall somewhere on this interval of 100 units. So I need 27 units. All right, so when we're looking at the all that stuff, 2.7, this is a 2-digit number. All right, and so if I'm going on that interval of 100 units, this would be halfway would be about, that would be 50 units. Here would be 25, and so right at this location here is where we would have 10.327. All right, so at this location, all right, that 2-digit number created that span between 10.3 and 10.7. And so when I say which is it closer to 10.3 or 10.4, I mean it in a figurative sense, like which one is it closer to? Is it 10.3, 10.4 in terms of the rounding, the 5 or above, give it a shove, but also physically as in a number line. 10.327 is actually physically closer to 10.3 than it is 10.4. So that's a visual way of representing it. All right. You know what? Let me do another one, because that is a good concept to really kind of drive home. So let me, I'm going to steal some more room, and both of these should make another iteration of the notepad. So I'll take this as a typo too. It's a brand new example. Let's say round, I'm going to still do nearest tenth, but a different decimal. Round 3.1695. That's enough. 3.1695 to the nearest 10. I didn't want to get too crazy. All right. So we highlight the place value that's important. In this case, the 1 is in the 10th place. And I just kind of move that. All right, we take a look at that 6, and I'll put the next value up. 2 is our possible value. So we're looking at that 6, and we're asking ourselves, is it 5 or above? So this is greater than or equal to 5 if we're using the proper terminology, but this is, I'll use more consistent verbiage here. This is 5 or above. So we give it a shove. So that becomes 3.2. All right. But that part, I mean, most people have experience with it. It's the number line part that people, it's like, if you're looking at anything on this, you're like, I don't really quite get that number line thing, so. So we're going from one possibility of 3.1 to another possibility of 3.2. All right. So all the values that follow after the 3.1, those are those make up the span between the two possible values, 3.1 and 3.2. All right. So that whole 695, everything left over. So all that stuff after all the numbers that we cared about ended, that 695, that 3-digit number, tells us that there's going to be 1,000-unit span between 3.1 and 3.2. All right. So a 3-digit number, you're talking about the thousandth place in decimal form. So that could be an indication of how you know that you're dealing with thousands, to 1,000 units. But you could also think of it as like, well, a 3-digit number, if it's going to be a fraction, it's going to be part of a whole. What is the whole? It's going to be 1,000, right? So 695, well, here's 500. All right, 500 units. That would be the equivalent of 3.1500, but I want 3.1695. So I don't know where that 695 is going to be, but I do know it's going to be to the right of that value. So I'll just call it like, maybe a little bit over. Somewhere over there, that's where 3.1695 is going to be. And the only question we have out of this is, which is it closer to, 3.1 or 3.2? All right. So that's the thing. You gotta start thinking about ways in which you can explain it, but you also have to think about ways that are acceptable for Common Core reasons. So they got to have some meaningful way of illustrating what the rounding approach looks like. The ladder technique is fine, but it doesn't always get at the underlying concept, right? So, so this is really the more appropriate technique. So it's something that you want to strive to try to get a handle on. All right. So, you know, they're not all that tricky. Some of them are pretty easy. Like if we're rounding 17 to the nearest 10, not the nearest 10. Sorry. Is there a question there? Oh, I thought I heard something. So if we're rounding 17 to the nearest 10, so not the nearest 10th, but the nearest 10, the tens place, all we're really asking us is which tens place value is it closer to, 10 or 20? And the answer is your rounded number. So this is actually much simpler, and we could even use the number line approach. And it should make a lot more sense because you're not dealing with the decimal values, but your possibilities are 10 or 20. Here's 15. So if I had to ballpark 17, I'd put it about right there, which is going to put me closer to 20. All right, and so that's all that it's really asking you to do. All right, but it does, like I said, get a little kookier when you start getting into the decimal values. All right, when teaching any concept, we want to make sure that we hit on the 3 major modes of mathematical content demonstration: computational and/or symbolic, graphical, and verbal. So that's the part where Common Core is always talking about writing an answer. So verbal, so they always say, give the answer and explain using numbers, words, or pictures. They try to keep it in simple terminology, but they're still getting at the idea that you need to not only just come up with the answer, but also why the answer makes sense. Yeah, so that bottom blurb is just a little justification there. So the examples on the next page, this is all just practice. And so the solutions are on the following page. So this is something that you can just kind of work on your own. It's not anything that you need really me to go over with you because, like I said, the answers are there. So that's really all that's going on for that stuff. So, you know, maybe I'll take a minute. Maybe I'll do a couple of them. All right, just so we have it. I don't want to totally shirk my responsibilities here, but it helps to have either access or a good understanding of the place value chart, right? Because that comes into play significantly, right? So, and we have that on other handouts, but it really just the idea that we're starting off after the decimal point with the tenths place, that there's no such thing as a 1/th place, that kind of makes all the difference, right? So, and really, I gotta hit this concept again because I think people definitely, I mean, they rely on technique and not necessarily true understanding. When we say that you have, for example, let's say you have 1.3245. All right, so something pretty simple. All of this stuff here, every single value here is a fraction of 1 unit. All right, so it's a fraction of 1 unit. So when you start thinking about what that means, you're saying you got 1.3245. When you're talking about money, you might say $1.32. But if you're cycling through decimals, it's like, okay, well, what does it take to get a whole number? After we hit 0.99, 99999, all those values, the next value up would be the number 2 if we're dealing with whole numbers, right? So we're accumulating decimal values until we have enough to gain another whole value, right? Another whole number value, right? That's what those decimal values are representing, right? So when I talk about a ladder or a number line or something like that, some people actually literally draw ladders in their classroom just to make it a little bit more user friendly. So if I have my ladder starting at 0, because it allows for maybe some negative numbers, but if you're at a young enough level, you wouldn't get into the negative stuff. But you would have 1, 2, 3, so 1, 2, 3. You're only about 30% of the way up when you're at 1.3245, right? So when you're at that location, you're not close enough to the next rung to get there. But every bit of space within this rectangle here, right, all of that space, that is equivalent to 1 unit. Right? The whole idea is in order to kind of graduate to the next level up, we have to gain 100% of that unit. And if we get that, then we can graduate to level 2 and then level 3 and so on, right? But it really is, it's that important, this concept of rounding. That's why I'm just kind of like just going nuts with it here. But in terms of actually computing the rounded forms, yeah, okay. I mean, as long as you know the place value, you're good. You can just follow the rules. But if you want your students to understand and not, and I think it's pretty important, you kind of have a responsibility to not make your students hate math. And when you mail it in on a concept and really don't take the time to try to explain it in a way that is true to its definition, but also accessible to all your students, then or even fake your way through understanding with it because you're not prepared, then you're doing your students and yourself a disservice. And not only that, you're guaranteeing that we're adding another person to the list of people who are going to hate math, right? Because math is specifically, I mean, I have a philosophical belief that everybody can be good at math. You just require the right teacher and a good motivator, good motivation, So if you want to be good at math and you have a teacher that's willing to explain it all and be patient, then there's no reason anybody can't be good at math. And so if you start just kind of glossing over definitions, just say, oh, just follow these steps and you'll get it. Or when tutors, I get tutors all the time that tell my students, oh, don't do it that way. That's so much harder. Just do it this way. Just type in these 3 things, you'll get the answer. My students come in like they're champs, like, oh, I learned this new way of doing it. It's so much easier. I'm like, that's not the point. The point's not easier. The point is to gain the knowledge and understanding of the underlying concept. If you don't take the time to really dive in there, then you're never going to understand the concept, right? So I just hit you with like 3 different ways to tackle rounding, but one of them is procedural. So when push comes to shove, what are you going to do? You got like, 20 problems here? If you really want to plow your way through them, and by the way, this is not something I'm collecting or checking. I gave you the answer key on the next page. There's no reason why you can't take your time with it. And if you want to take the whole semester, take your time with it, go for it, but you could just say, all right, yeah, that's the value that's in question. I'm looking at this guy. What's that rule again? 5 or above, give it a shove. All right, this is 5. So that means that 2 is going up to 3. And so this would round to 30. All right, cool. Now, if you understand the underlying concept, then shortcuts are a great thing because it's a time saver. But that's your reward for already knowing, having a deep understanding of the material. But if you don't, take your time and say, okay, I'm not really sure where this is going to go. So what are my possibilities? my possibilities are I could stay put at 25. Well, it's nearest 10th, so my possibilities are I can go down or up. I said 10th, I mean 10th, please. Or you can go up. All right. So those are my two possibilities. The 25 goes right in the middle. Now, if you're just following the rule and you get the answer, then I don't think you ever get to this little sticking point in the process. Okay. So 25 is precisely halfway between 20 and 30. If the definition is saying that rounding is just telling you to put the value that the given number is closer to, if it's precisely in the middle, which one is it closer to, 20 or 30? All right, it's closer to neither. So what's the rationale behind selecting 30? You know, aside from saying if it's 5 or above, give it a shove. All right, and the short answer to it is, and this is my least favorite part about math in general, is that really what happens is the first person that gets to a concept, meaning like the first person who publishes rules related to a concept. You know, you go back in the day when mathematicians had like math battles with one another. You know, it sounds really nerdy, but that's how they made their money. And so you know, like you became famous because you beat some other mathematician in a competition. You challenged them basically to a math duel. All right, and so what happens is the first person that got to this concept decided, all right, well, if it's halfway, it could go either way. Let's just go up. Everybody, we're going up. That's the rule. That's the rule I decided. All right, and it's like, well, who said you can decide? Well, you see my name on that paper right there? And nowadays it's like, you see my name on that website that talks about this material? Well, I don't see your name on a website. You know, I don't see your name in a textbook. So my way is the right way. Well, what's your reasoning for going up as opposed to going down? And I'll tell you, here's my reasoning. Imaginary coin in my hand. Flip. We're going up. That's all it was. All right. So the person who got to this concept first decided that if it's 5 or above, we're giving it a shove, maybe because it rhymes. You know. So that's really all there is to it. Because it could go the other way. If you're approximating, you could easily say, well, I don't know, I like the number 20 better than 30, so I'm going to just take that one. All right. The 10,000s place. So I'm going to work across. So I'm just going to do a couple of them, the ones that are kind of like the sticky ones. All right. So this one is good because I can do some labeling here as soon as I take a swig out of this water. I've been holding this water bottle in my hand for like 20 minutes and still hadn't taken a sip out of it. Okay. So here's my 10th. Let me make that a little thinner. Hundredth, 1,000, 10,000. And then 100,000 and so on, but I only need 10,000. So once you get the little naming convention here, then you know it's just proceeding from there, as long as you know you're not starting with the ones place. Right? So when you take the skills assessment on the 6th of October, you're going to see that there'll be some multiple choice questions in there. And I can guarantee you that a question is going to say round the number to the near, or which of the following is the number rounded to the nearest 10th. And I'm going to put a number where it's rounded to 2 decimal places as a choice. And my hope is that me talking about it right now is going to allow for this to be the first time ever that people don't select that answer. But for whatever reason, people just cannot stop themselves when they see a question asking for the 10th or 10th place, they go 2 decimal places. Right? It's just not right. All right. So if I'm rounding to the nearest 10,000, that's this key value. And so I'm focusing on the first value afterwards. That's definitely above 5. So that's 5 or above. Give it a shove. Right? So we're going up to 6. And so therefore, you don't have to use the notation for therefore. I just like doing it. 3 dots in the form of a triangle means therefore. 1.0006. I'm going to use the fancy box. Let's make it look a little nicer. A little bit better. Make it look with that. All right. So it's not too bad as long as you know the naming convention. All right. So same idea for the next one, 100th, you know, J right below it. As long as you know where the 100th place is, you're fine. All right. If you're going to the tens place, like in K, you just got to remember that the tens place is not the same as the tenths place. All right. So this is the tens place. So we have ones. I'll just jot it on the side here. All right. So as long as you don't misread that, because this problem is designed to kind of be a trick question. It's not really a trick question. It just tricks people because you see the decimal, you see 10, and it doesn't even like register that that doesn't say 10th place. You just see the decimal and you think that it must be that. Right. So that that important value, that 1 is the one that we're looking around. The this number here is 5 or above. So we give it a shove on up to 6. Well, sorry. We give it a shove on up to 2 because we're rounding to the nearest tens, not the nearest ones, and it wouldn't have even been right if it was the 1. So I don't even know what I was thinking there. So this would be 20. But I think this is a good example when it comes to, you know, asking your students to justify their answer. I think this is like a good exemplar problem because again, that little trick there, because maybe it doesn't trick adults, but it might trick kids. And it's not so much a matter of like, let's trick them, those little bastards. No, it's not like that. It's more like, if they can avoid getting tricked, then they really understand the concept, right? That's really what it comes down to, right? But the number line is a really good strategy for this one because if they draw an appropriate number line, again, the possibilities are 10 and 20. 15 would be smack dab in the middle. I don't know precisely where 15.0293 would be, but I do know it's got to be to the right of 15, right? Because the numbers get larger as you go from left to right. And you could also be reinforcing that concept with the students as well, right? The numbers are getting bigger. So where would the 15.0293 fall? It's going to fall to the right of the 15. That makes more sense. And so which number is it closer to? The 10 or the 20? Logically, conceptually, graphically, it makes sense that it would be the 20. All right. So then you have all these other problems. Some of them are a little bit more straightforward, but let's take a look at number G. Number G. Now I'm definitely becoming an old teacher. Yeah, that would be letter G. So for G, it says round it to the nearest ones place. So again, the ones place right there. So the number after it, you know, it's 5 or above, give it a shove. So this one is important for students, so 5 or above. This one's important for students for a couple of reasons. And the one big reason is because it tells us that rounding can happen, it can cross over a decimal point, right? So taking that 9 and making it go up to a 10 is an important idea. But because of that 10th place, that 9 in the 10th place, that allows that to happen, right? So that's an important piece. But also, like it's telling us to take this 9 and raise it up to 10. But 10 is a 2-digit number, so that's not going to fly, right? So when I take a 9 and replace it with a 10, I'm really just taking the 9, replacing it with a 0, and I'm adding the 1 part of 10 to the 8, all right? So it's kind of strange when you think of it that way, but it's kind of like, well, it's 2 digits, so I'm going to associate the 0 with the 9 and the 1 with the 8. So I have 489.9, all right? So instead of looking at it as a 10 just right over the 9, I might look at it like this. So the 9 becomes a 0, and these two get added together. But that's pretty darn confusing even for adults. So this is a classic example of where a number line is not only a pretty good idea, but it's pretty necessary, right? Because my two possibilities, if I'm rounding to the nearest ones place, would be, just counting by ones, 489, 490. All right. So right smack in the middle is where 489.5 would be. I don't know where 489.9 is, but I know it's got to be east of the 489.5, so it's going to put it like right over here-ish. So again, if my choices are this number or this number, which one is it closer to? It's going to be this one. I think this is one of those cases where if you try to do it numerically, you might cause more confusion. So what we're looking for, in addition to being able to just follow rules to get an answer, is for students to develop the flexibility to be able to say, you know what, I think this is a graphing situation, rather than a computational situation. So when we hit those 3 modes of demonstration of knowledge in mathematics, when we talk about the verbal, the graphical, and the computational, so like we're kind of enforcing that, but the idea is that down the line they would take that upon themselves, right? So they would decide for themselves why they would end up deciding to do it one way as opposed to another. And it's really, really hard. And I would say probably 20 years teaching, that's been kind of like the biggest bugaboo, where you teach people how to do things manually, as in like computationally, crunching numbers, using calculators and stuff like that. And then almost as like kind of an add-on at the end, you throw in a graphical approach. And that graphical approach is like, all right, well, it's just there. It's just, okay, we could also do it graphically. And the students are like, well, okay, I already just learned that other thing, so my brain's full, so yeah, cool, there's a graph. I don't know that I'll ever need that. Instead of just having it as an add-on at the end, have it as an interconnected part of the process, right? So, because, and I can tell you, my students, my son, other students that I've polled over the years, they all say the same thing. It's like when they've always been working with the graphical approach, throughout their learning, it always makes sense when it comes up on a test, where it's like, okay, well, why wouldn't it come up on the test? We've been doing this all along, and I'm kind of wired to think this way. The students who are very resistant are the ones that have it kind of tacked on at the end. Okay, let's talk about graphing for like 30 seconds. Then it comes up on a test, and they say, well, I don't know how to answer this. And the teacher always says the same thing. Oh, we covered that in class. Student replies, when did we cover that? Oh, it was on Tuesday, September, blah, blah, blah. And the student says, maybe I was absent that day or something. And the teacher says, well, we covered it. They're neglecting to say that they covered it over a span of 30 seconds at the end of a class period after they went over something really complicated. So, you know, like there's little bits and pieces that kind of detract from the learning process, and we want to avoid those sorts of things. So the graphical part is resistant as many people are to it. Teachers just as much as students, it needs to be there. You know, there's no way around it. You know, I mean, maybe not this particular graphing technique, but a visual component, because the alternative is to write out the thought process. Now, there is a time and a place for that, but the danger of a verbal response for a question like this, and so I'll preface what I'm about to say with, you're taking this class, again, I mentioned before, some of us need 3 credits, and some of us, we really want to be able to use this in classes, and, you know, we want to be math, you know, elementary teachers, preschool teachers, and we're going to involve some math along the way. Okay, so we're generally, and I could be wrong in some cases, we're not masters of literature in most cases, math teachers, right? So, yeah, okay, so like me, I can string a bunch of words together and make a sentence. I've even been known to tell a story or two, but in terms of like writing math, but in a literary sense, you know, like main idea, body, conclusion, you know, supporting details and all that stuff. Even when math teachers try to do that in a class, it doesn't end up the way they want it to, right? So when I ask a student to explain their thought process and how they solved question G on this page, what they're going to say is they're going to say, well, I highlighted the 9 to the left of the decimal point. Then I looked at the 9 to the right of the decimal point, and I saw that that was 5 or above. So I gave the 9 to the left of a decimal point, I gave that a shove, making that a 10, put it together, and it became 490. And so what did they do? They just restated the process without adding any of their own individual thoughts, their rationale into their explanation. So it's not a meaningful explanation, right? So if I were to say, tell me how you find the factors of a number. If your explanation is step 1, do this, step 2, do that, step 3, circle your answer, that's not a real explanation. But a lot of people accept that for full credit, you know, and it shouldn't be. It's just they don't know what they should be looking for. So I really mean it when I say a picture's worth 1,000 words, because if you have a good diagram, it's going to explain, especially on the young ages, it's going to explain what they don't have the vocabulary to articulate. Right? They're never, I never say never. They're not often going to have the means to be able to articulate how they knew this should have been 490 without some sort of resource, and that resource would be a diagram of some capacity, right? So very important. I'm spending a lot of time on this because that's how important I find this material to be. And, you know, speaking as a person who, you know, teaches I mean, all different levels, you know, all the way up to, I mean, I'm teaching college classes, but I teach the high level calculus classes. I teach the remedial courses. I teach everything in between, you know, young, old, everyone. This concept, it's always going to be a part of it. And it's not just going to happen in math classes. It's you know, a transcendent concept. it passes beyond the borders of just mathematics, you know, in terms of curriculum. So yeah, hitting this concept hard in your class is very, very important because it gives them a good foundation. You know, it's kind of like if you think about, like, you would never just jump into, okay, how do you add fractions? You would never just do that with elementary school students. You would start off with, like, here's a circle. Show me what half of that circle looks like. Show me what a quarter of that circle looks like. You start getting into hands-on stuff. You know, why would this be any different, right? So that's the moral of the story there. All right. So I'm going to stop this recording.